Assalamualaikum. So today I and my team members will present about the FEA analysis of bike frame. So the name of our design is the fusion bike. For the background, this project focuses on the bicycle frame as the main structural component that affect handling, comfort, and overall performance. With the use of CAD tools and finite element analysis, the frame design can be optimized to withstand real-world loading conditions. FEA helps to identify stress, hotspots, deformation zones, and fatigue area. This study also compares material like aluminium and carbon fiber to evaluate the performance under the same conditions. Overall, simulation-based design improves safety, durability, and ensure the frame meets industry standard.
For problem statement, modern bicycle frame face a variety of complex and dynamic loading conditions. They not only need to perform well, but also ensure structural strength and rider comfort. However, traditional design methods are often not enough. They struggle to identify areas of high stress and deformation in area work scenario. This becomes even more complicated when different material and frame shape are involved, which can affect durability, safety, and overall ride experience. Therefore, we need a more systematic and computational approach to evaluate and optimize bicycle frame design so they can meet the high demand of modern cycling environments. Okay, next, the objective. The study aims to design a modern bicycle frame using SolidWorks and evaluate its performance using finite element analysis, it means FEA, in assist under 3 different real-world loading conditions. Okay, so the first one, we will design the frame based on current industry standard and optimize the geometry. The second one, we will perform simulation in ANSYS to analyze how the frame behave under different loading scenario. And the last one, we will evaluate the stress, deformation, and safety factor using different material to find the most optimal design in terms of strength, comfort, and safety.
So, literature review. I will explain about the Distracker 700C frame set, high-face black. So, the purpose of this frame is designed for long-distance touring and daily commuting, reliable under full load on mixed terrain. The material using chromoly steel for high strength, flexibility, and shock absorption. The frame design is shorter chain stays for improved control, lower bottom bracket, enhanced balance and handling, slope top tube, improve standover clearance. For the mounting options, multiple mount for racks, fenders, water bottles, and lights for touring friendly. For the axle system, 12 mm through axles, enhanced frame stiffness and load supports. For the tire clearance, fits up to 47 mm tires, which is for this frame, or 2.1 inches tires, which is 26 inches with fenders. Okay, for 2023 Richie Action frame set, the purpose of this frame is designed for adventure riding, bikepacking, touring, and commuting. For the frame material is heat-treated triple butt logic steel tubing, and TIG welded for a strong yet lightweight frame. For the fork, it uses a Richie steel fork with multi-purpose mounts, compatible with racks, fenders, and dynamo lights. For the mounting option, it uses rack and fender mounts, extra mount under the down tube, triple mount on fork legs for carrying gears. For the brake and axle compatibility, post-mounted disc brakes and use 148 mm rear axle spacing. For the bottom bracket, it uses 73 mm English threaded, and then the tire compatibility is 27.5 inches times by 2.6 inches or 29 inches times by 2.6 inches tires. For the design compatibility, for the design flexibility, It uses a flat bus with 27.5 inches wheels for trail use, and then use drop bars with 29 inches wheels for rough road touring. For the weight, its frame around 2,400 grams, which is size L without XL, and then the fork is around 1,125 grams for uncut steerer. For the crankcase range, the single crankset range is 24 to 40 T, and for the double is 24/34 to 28/38.
Alright, now I will explain the methodology used for FEA estimation of the bicycle frame. First, the bicycle frame was modeled in SolidWorks, consists of the key structure, head tube, seat tube, bottom tube, seat stay and chain stay. And then the model was imported into ANSYS for simulation and analysis. A 20 mm element size was applied, resulting in over 37,000 elements. The frame material used is aluminum alloy, chosen for lightweight and corrosion resistant, which makes it ideal for bicycle application. We assume a rider weight of 70 kg, which is equivalent to 689.7 Newton under set. Alright, for this study, we tested the frame under 4 loading scenario, which is each designed to represent real life riding condition. These are: first is case static, which is simulating the rider sitting on the saddle. Case number 2, front bump, simulating an obstacle impact on the front wheel. Rear bump, simulating a bump impact on the rear wheel. The last one is climb while standing, which is simulating a rider pedaling while standing on 20-degree slope. In each case, we apply a load of 260 Newton, which is 3 times of a rider weight. This account to extreme condition like impact and aggressive climbing. The boundary condition include fixed support at the wheel and load application at the point like seat post, bottom bracket and head tube. Before running the full simulation, we perform manual stress calculation as a reference to validate the simulation result. We use the basic stress formula, sigma equal force over area. The calculated stress for each case are shown in the table. First, the static load at the seat tube gave around 5.12 megapascal, front bump 5.17 megapascal, rear bump the highest stress 13.11 megapascal at the rear dropout. The last one is the climbing give the lowest, around 4.31 megapascal. This value had ensured that the FEA model was set up correctly before moving to detailed analysis.
For this slide, we analyzing the safety factor based on total deformation across 4 different loading conditions. From the visual comparison and simulation results, we can see that the front bump case caused the most significant deformation on the structure. This suggests that it the most critical scenario in terms of frame replacement. The deformation patterns shown in the simulation image highlight which parts of the structure are most affected in each case. The red areas represent zones of maximum deformation. Next, we look at the safety factor based on equivalent stress for the same 4 cases. Again, the front bump scenario stands out as the most critical, producing the highest stress level on the structure. This indicates that it the most demanding condition in terms of structural strength. The simulation visuals show the stress distribution across the frame, where the red area mark the location of maximum stress, potential weak point in the design.
Safety factor focus on the minimum safety factor within each load case, pinpointing the weakness structure point. The front bump can show the lowest minimum safety factor, reinforcing its role as the most critical scenario. Rear bump is slightly better but still concerning. Static and climbing case show much safer value. This graph is useful for identifying localized failures under peak forces and support our design improvement recommendations. In conclusion, the FEA of the fusion bight frame identified critical stress and deformation zone under realistic loading. This study confirms that simulation-driven design improves structural performance, supports material optimization, and enhances frame safety and durability according to industry standards.